Good morning, everyone. My name is Emma Verde, and today I will be presenting our work titled Design and Selection Methodology of an Electromotive System for Internal Combustion Vehicle Retrofit. This research, developed at the Instituto Politécnico Nacional in Mexico, proposes a generic, parameter-based, and modular engineering methodology centered on a vehicle control unit architecture. The methodology was validated on a compact sedan, achieving 133 watt-hours per kilometer and approximately 85% overall system efficiency. Let's get started. Introduction. The case for retrofitting. Transportation remains one of the largest contributors to global carbon emissions. While full electric vehicle adoption is the long-term goal, large-scale EV fleet replacement is constrained by both economic barriers and infrastructure limitations, particularly in developing urban contexts. Vehicle retrofitting, that is, converting existing internal combustion engine vehicles into fully electric ones, emerges as a scalable and cost-effective intermediate strategy. It extends vehicle lifespan, reduces material waste, and lowers environmental impact without requiring entirely new manufacturing chains. Our work addresses this challenge by defining a generalizable, experimentally validated methodology that guarantees dynamic compatibility, energy efficiency, and electrical safety through a modular vehicle control unit architecture. State-of-the-art critical analysis. When reviewing existing literature on EV retrofitting, we identified three critical limitations that constrain the applicability of current approaches. First, simulation-only studies provide useful preliminary insights, but systematically ignore real-world constraints such as mechanical coupling tolerances, auxiliary system compatibility, and thermal or electrical safety under actual operating conditions. Second, studies with an isolated subsystem focus, addressing only the battery or only the motor, lack a unified control strategy and cannot be replicated across different vehicle platforms. Third, the absence of modular control architecture in most approaches restricts scalability, prevents future upgrades, and limits experimental validation under real driving conditions. These gaps motivated the development of our integrated methodology. Comparison of EV retrofit approaches. This table summarizes how existing approaches compare against our proposed methodology across 5 critical dimensions: simulation basis, experimental validation, dynamic energetic integration, modular VCU architecture, and parameterizability. As you can see, simulation-only studies lack experimental validation and modularity. Battery-focused and motor-focused methodologies offer partial integration but no modular control. Experimental retrofits without a VCU fail on integration and parameterizability. Our proposed methodology is the only approach that fulfills all 5 criteria. Offering full experimental validation, complete dynamic and energetic integration, a modular VCU architecture, and a parameterizable design applicable across vehicle platforms. Proposed methodology, 5-phase framework. Our methodology is organized into a 5-phase structured framework designed to be reproducible and applicable across different vehicle configurations. Each phase has clearly defined inputs, processes, and outputs. The process flows from vehicle characterization to dynamic and energy modeling into powertrain component selection, VCU-based electrical integration, and culminates in experimental validation under real driving conditions. This modular structure ensures that any engineering team can replicate the methodology independently, regardless of the specific vehicle platform being converted. Methodology phases, inputs and outputs. Let me walk you through each phase briefly. Phase 1, vehicle characterization. Starting from vehicle mass, gearbox ratios, and target performance, we identify the mechanical and dynamic parameters of the base platform. Phase 2, dynamic and energy modeling. Using those parameters combined with a representative driving cycle, we compute the torque, speed profile, and total energy requirements. Phase 3, powertrain selection. Based on the modeling results, we select the motor, inverter, and battery pack specifications. Phase 4. Electrical integration. The selected components are integrated through the VCU architecture, defining the complete electrical system layout. Phase 5. Experimental validation. The integrated vehicle is tested under real driving conditions to evaluate performance against design targets. Reference vehicle and design requirements. As the validation platform, we selected a 2002 Ford Focus sedan with manual transmission. This vehicle is representative of compact urban mobility with a well-documented mechanical structure. Key parameters of the base platform include an original ICE peak power of 130 horsepower, or approximately 97 kilowatts, a maximum torque of 183 newton meters, a post-ice removal vehicle mass of approximately 1,000 kilograms, and an average urban power demand below 25 kilowatts. These parameters directly fed into Phase 2 of our methodology to define the electrical powertrain requirements. Electric motor selection. For the electric motor, we selected a 3-phase asynchronous AC motor, chosen for its robustness, minimal maintenance requirements, and native support for regenerative braking, which is critical for urban stop-and-go efficiency. The selected motor delivers a nominal power of 15 kilowatts, a peak power of 45 kilowatts at 100 volts AC, and a maximum torque of 165 newton meters available from zero speed, ensuring strong initial acceleration without gear shifting penalties. As an electrical consistency check, 100 volts multiplied by 450 amperes peak current confirms the 45 kilowatt peak power rating, validating the component selection. Regenerative braking. Regenerative braking is a key efficiency feature of the system. During deceleration events, the motor operates as a generator, converting kinetic energy into electrical energy that is returned to the battery pack via the bidirectional inverter. In our measurements, negative power values in the acquisition data correspond precisely to these recovery intervals. In urban driving conditions, characterized by frequent stops and low-speed deceleration, regenerative braking recovers between 8 and 12% of energy that would otherwise be dissipated as heat through mechanical brakes. This translates to an average increase of approximately 10% in driving range under urban cycles. Battery pack design. For energy storage, we selected lithium iron phosphate, LiFePO4 chemistry, chosen for its high thermal stability, long cycle life, and significantly reduced thermal runaway risk compared to other lithium chemistries. The battery pack is configured with 30 cells in series, each at 3.2 volts nominal, yielding a nominal bus voltage of 96 volts DC. Cells are rated at 100 ampere hours, supporting discharge rates up to 3C. This gives a total usable energy of 9.6 kilowatt hours. At an average power demand of 7 kilowatts in urban conditions, the system provides approximately 62 kilometers of autonomy at 45 kilometers per hour, well suited for typical daily urban commuting patterns. Battery management system. A battery management system is mandatory for safe and reliable operation. Our BMS performs 4 essential functions: cell monitoring, continuous voltage and temperature surveillance across all 30 cells; cell balancing, equalizing charge distribution to maximize pack capacity and extend cycle life; thermal and overcurrent protection, active fault detection with automatic shutdown to prevent unsafe conditions; and inverter communication, coordinating energy flow during regenerative braking events to ensure safe current return to the pack. The BMS is the critical safety layer between the energy storage system and the rest of the powertrain. Power inverter selection. The power inverter converts DC battery power into variable frequency AC current for motor control. It must operate within a 100 to 120 volt DC input range and deliver output currents exceeding 300 amperes. We validated the current rating analytically. At 45 kilowatts peak power and 90% inverter efficiency, applying the 3-phase power equation, we obtain approximately 289 amperes, confirming the selected component rating. Beyond electrical performance, the inverter supports bidirectional power flow for regenerative braking, complies with ISO 6469 electrical safety standards, and integrates with the vehicle monitoring network via CAN bus communication, enabling full coordination within the VCU architecture. System integration and safety. The complete electromotive system integrates the electric motor, bidirectional inverter, LiFePO4 battery pack with BMS, and a digital dashboard displaying real-time speed and state of charge. Mechanically, the motor is coupled to the original gearbox through a custom fabricated steel adapter plate, preserving the existing drivetrain and enabling retention of the manual transmission. From a safety standpoint, the integration requires proper high-voltage cable insulation, correct conductor sizing for peak currents, active thermal management, and full adherence to automotive electrical safety standards throughout the vehicle. Experimental results: energy consumption. Moving to experimental results. Energy consumption was measured during real urban driving using onboard voltage and current acquisition synchronized with vehicle speed data. 3 urban cycle tests were conducted. Test 1, 12.4 kilometers, consuming 1.65 kilowatt hours, yielding 133 watt hours per kilometer. Test 2, 11.8 kilometers, 1.59 kilowatt hours, 135 watt hours per kilometer. Test 3, 13.1 kilometers, 1.71 kilowatt hours, 131 watt hours per kilometer. The results are highly consistent across all three tests. The average consumption is 133 watt hours per kilometer, overall system efficiency is approximately 85%, and the urban range reaches 62 kilometers at 45 kilometers per hour average speed, meeting the design targets established in Phase 1. Energy consumption versus average speed. This graph plots energy consumption against average vehicle speed. The results show a stable consumption region between 40 and 50 kilometers per hour, which corresponds precisely to typical urban driving conditions. The minimum observed consumption of approximately 133 watt-hours per kilometer confirms that the system operates near its optimal efficiency region within this speed range. As expected, consumption rises at higher speeds due to increasing aerodynamic drag forces, a behavior consistent with the longitudinal dynamics model developed in Phase 2. Instantaneous power demand, regenerative braking effect. This figure compares instantaneous power demand with and without regenerative braking enabled during an urban test cycle. The negative power intervals visible in the trace correspond to deceleration events where the motor operates as a generator. During these events, kinetic energy is captured and returned to the battery via the bidirectional inverter. These recovery events account for the 8 to 12% energy recovery reported earlier and are directly responsible for the extended range performance observed in our urban test results. Benchmark, comparison with reference EVs. To contextualize our results, we compared our system's energy consumption against reference values from literature and commercial EVs. Typical compact commercial EVs consume between 140 and 160 watt-hours per kilometer in urban conditions, with vehicle masses between 1,200 and 1,400 kilograms. A comparable retrofit study from literature reports 150 watt-hours per kilometer at 1,050 kilograms. Our system achieves 133 watt-hours per kilometer at 1,000 kilograms, the best result in the comparison. Three factors explain this performance: maximum torque availability at low speeds, minimizing acceleration losses, retention of the manual transmission keeping the motor near its peak efficiency region, and regenerative braking recovering energy during frequent urban deceleration events. Scalability and generalizability. A key contribution of this work is its scalability beyond the specific validation platform. The parameter-based design approach allows the methodology to adapt to different vehicle configurations simply by scaling battery capacity and motor power, without modifying the core VCU control architecture. The modular VCU enables coordinated management of propulsion, energy storage, and auxiliary systems across compact, midsize, and heavier vehicle classes. And the explicit definition of phase inputs and outputs ensures that other engineering teams can replicate and apply this framework to future retrofit projects independently. Conclusions. In conclusion, this work presents a modular, parameterizable, and experimentally validated VCU-based retrofit methodology that integrates vehicle dynamics, energy performance, and electrical system design, directly addressing the main limitations identified in existing approaches. Experimental results confirm stable and consistent energy performance, 133 watt-hours per kilometer and approximately 85% system efficiency under real urban driving conditions. Future work will extend the methodology to different vehicle classes, incorporate longer-term durability assessments, and evaluate performance across broader driving cycles, including suburban and highway scenarios. This methodology represents a scalable, validated alternative to conventional electrification strategies with practical potential to accelerate EV adoption and reduce urban greenhouse gas emissions. Acknowledgements. The authors gratefully acknowledge the support of the Escuela Superior de Cómputo, the Escuela Superior de Comercio y Administración Tepepan, and the Red de Expertos en Innovación Automotriz, all belonging to the Instituto Politécnico Nacional of Mexico, for the facilities and institutional support that made this work possible. Authors, this work was developed by a multidisciplinary team from ESCOM and ESCA Tepepan at IPN. Our contact information and ORCID identifiers are listed on screen for anyone interested in further collaboration or questions. Thank you very much for your attention. We are happy to take any questions from the audience. This work is available for discussion, and we welcome any feedback from the community working on vehicle electrification and sustainable urban mobility.